Hi, welcome to this module on metals as part of this course on basic construction materials. In the first part of this module, we will today's lecture, we will look at iron products and steel. Essentially, we will be talking about how they are manufactured and some basic properties of these materials. And in the future lectures, we will look at steel reinforcing bars and structural steel also. These are some of the books and all that I have been using, and essentially a lot of material from the internet have been used for this particular lecture. Now, what are the various iron products? They include pig iron, then cast, ductile and wrought iron. These two we will be covering today. Okay, and steel reinforcement and structural steel will be covered in the subsequent lectures. But these are the major iron and steel products or iron products. Steel is essentially made of iron with some other materials. Okay, so iron ore is used to manufacture the product iron, which we call, what is it used? Iron ore, hematite. And India contributes about 5% to the world's iron ore output. That means, this is a photograph of a mine in Australia, and you can see here this pie chart on the left side, which kind of shows how much is the production or contribution by various countries towards the iron ore extraction. Okay, you can see that Australia plays a major role, about 35%, and India is about 5% of the total iron ore which is produced or supplied in the world is from India. So, we are not a small player, definitely have significant stake on this. Now, let us look at how is iron actually made. It's first the iron ore is put into the blast furnace. So, you can see the picture here on the top right. This is how a typical blast furnace would look like. It's a huge structure which will be typically about anywhere from 30 to 60 meter height. So, depending on the capacity, etc. So, you can see here the raw materials are piled here, you can see, and then there is this conveyor belt which takes the raw material to the top, and here also another conveyor belt which comes to the top, you can see, and then at the top it's dumped into, you can see here it's dumped into the hopper, and actually here they are stacked inside this furnace. Like I said, this is about 30 to 50 meter high, 60 meter high, and you have lot of material volume you can occupy here. So, these materials are stacked inside this furnace, and then you have this hot air blast. That is why it is called blast furnace. So, hot air is blasted from the bottom, and the material, I will show you in the next slide, but you can see here the material inside here inside the furnace get heated up, and then it reacts and then starts melting, and you get the iron, molten iron at the bottom, and also some slag is formed or floating on the iron. So, a molten iron that slag is also used for other purposes. So, you can see here all additional part of the furnace which helps in completing the process. You can spend some time on reading each of these items and try to understand what each of these are for. Now, the process inside the blast furnace, that is I am showing another photograph here. Again, all these are from the internet. You can look at these addresses which I have provided at the bottom of the page to get more details and to read more about these images which are explained here. So, here first you have a stack of raw materials, like this is the image of that hopper which I showed in the previous slide. So, you are putting the iron ore, typically hematite, then coke and limestone. So, all these are dumped through or placed through this hopper and stacked here inside the furnace. Okay. And then what you do is you have this hot air blast, which is here at the almost at the bottom of the furnace, and then because of this hot air there is temperature variation. As you can see here at the bottom, it is 1500 degrees Celsius. As you move up, 850, 700 and up to about 250 degrees Celsius at the top of the furnace. Okay. Now what these temperature differences does is, let's look at here at about 700 degrees Celsius range, the iron ore gets reduced to Fe in the liquid stage and the carbon dioxide. And then what happens is, as the temperature increases, you also have carbon dioxide reaction and reduction of iron ore, and limestone also decomposes at this temperature. At about 700 degrees Celsius, you have reduction of iron ore. As the temperature increases, as you move down into the furnace, you also see that limestone starts decomposing, and what is formed? Slag is formed. Okay. Now, as the temperature keep on increasing as it goes down, the slag and everything starts really melting, and then you can see the molten slag will fall down and then settle here, or rather float on top of the molten iron. So, molten iron being heavier, it will settle down, and molten slag being lighter than the molten iron, it will float on top. Okay. So, what is in the slag? You can see the formula here, calcium silicate oxide. Okay. And this slag is taken out to produce, it's used for actually even for cement manufacturing nowadays. Okay. And then you have molten slag over here, and that's used for making pig iron. So, you can see here, this picture over here is indicating this point here. Okay. Molten slag is taken out and then ladle, and then it is poured into forms to make pig iron like this. I will show you more detail about that. Now, this is the picture of an old pig iron casting mold. You can see on the left side. And first, let us see why it is called pig iron. Okay. It is because the shape of these pig iron pieces, they kind of, or this mold area, they kind of look like baby piglets being breastfed. You can see the picture here. So, you can see one main channel here through which the molten material is poured, and it flows down and then flows to the left or right. As you can see in this black and white picture on the left side, you can see that the hot material or the molten iron is flowing down and then flowing into these small molds on the in that area. So, similar, this kind of picture, this somewhat represents, or not represents, it resembles the, if you take a photograph of this piglets being breastfed, it will somewhat resemble that, and that is how the name pig iron, people started calling it pig iron. There is also another story by which they say that the face of the very old pig iron, the molds, they look like the face of a pig. Okay. I do not have that photograph here, but that is also another thing which, if you read in the internet, you will find that these are the stories behind the name pig iron. Now, you can also see how big the the furnace looks like here. You can see the large size, and you can compare that with the size of the human beings or people standing there. Now, this is a modern pig iron casting mold, where again you can see molten material on the left. You can see here molten material being poured, and then it flows down and then it flows. Now, here this is actually a conveyor belt. It is not that this molten material is flowing all the way till here, but it is rather taking its position in one of the molds, and then it's transported, it's transported using kind of a conveyor belt. And you can see on the right side picture also, the molten material is poured into this, and then it settles, and then it is taken out, using a conveyor belt. So, the technology has changed a little bit. In the first one which I showed in the previous slide, it was more of the material flows all the way to the mold. Here the material flows, but then it is taken using a conveyor belt. So, there is a little difference in that. Now, let us look at what is the composition and key properties of pig iron. It has about 90 to 95% of iron, and then 3 to 4% of carbon and traces of various other materials or other elements such as silicon, manganese, phosphorus, etc. So, this is a typical photo or how this pig iron would look like. Of course, it depends on the shape of the molds, and you can see this tapered shape, so which makes it easy to be lifted out of the mold. Now, not well controlled manufacturing, as you have seen, this is not really a well controlled manufacturing process, because this hot molten material is poured into the molds or pigs and then it is taken out, and it is harder than 100% pure iron. So, hardness is very high because of the presence of high concentration of carbon, about 3 to 4% of carbon. Okay, that is why this is harder in nature, and then also lower strength because it is very porous in nature. Because as I said, it's the manufacturing process itself is not very well controlled. So, because it's porous, low strength, high hardness, mainly low strength, it is the products which are coming out of this are not really of high quality in it. So, you will see sometimes all these type of fasteners or low cost products which are good enough for those particular applications, but not necessarily for all the applications where you really need higher strength material. Okay. So, these pig iron products are not very high quality, but you have to see whether for that particular application whether this is sufficient or not. If not, you have to go for other products. Now, another more refined product is cast iron, where cast iron is used for pipelines, water pipelines, sewage line. I mean, many products are there. You can see here pipeline, and then these are some of the connections for the pipes, and wherever there is a complex shape, and then that shape can be achieved by making a mold, that is where cast iron comes into the picture. Okay, and then pipelines, because it used to be very comparatively high strength than the other material than the iron, so people started using cast iron. But there were some problems, I will come to that later, and these are other examples of cast iron. Of course, corrosion is an issue, but it is not as, because it corrodes relatively less than the steel, but still there are other mechanical related problems like brittleness. So, I will come to that later. And then also when you have very complex shapes, there cast iron is very widely used, because it is very easy to make those. So, you can see here this also, like once you have a mold of that particular shape, then you can make this product. So, here also when other examples where you have complex shapes, cast iron can definitely be used, including cookingware. Now, why is it a better as compared to pig iron? Because of better manufacturing process, I said already. Now, here you can see a photograph where the mold on the left side, molten iron is being poured into iron plus carbon. Okay, it is being poured into the cast or into the mold. You can see here, this is the mold. You can see a lot of like a assembly line. Okay. Now, on the right side, it is more clear on how these molds look like, and these molds are made out of foundry sand. Okay. This is the foundry sand you see on the top right image, the foundry sand which has clean, that means there is no clay particles in that, and it is uniformly sized, or uniform gradation, and silica sand typically. So, also main other important property of this foundry sand, it should be cohesive in nature. In other words, it should held together and then form that shape or complex shape whatever is required once it is molded into that shape. It should not just fall off. So, you need very high cohesiveness also. Okay. So, mechanical interlock plus cohesiveness plays a role, and then it just holds things in place. So, this is a typical how the foundry sand look like. You can see here there are some cast or shapes of foundry sand, and then the molten material is poured into this place here, and it flows and then makes the shape. And this is an example of, on the bottom you have an example of something which looks like a wheel shape or whatever machinery parts. Okay. So, this kind of complex shape whenever you see, you can think that most often it is made out of cast iron, because you have high strength. Main problem is brittleness. Okay. So, but still it is widely used in many applications because of the easiness to make it also, to get the complex shapes. So, these are again some of the applications. You can see pipelines, drainage pipes, sewer lines, and then also machine parts. Now, composition and key properties of cast iron: iron plus up to about 4% of carbon, that is the key ingredient which gives its the properties, and because of this you get high strength and high corrosion resistance and high brittleness. So, this is the problem. Okay. High strength and high corrosion resistance are very good, but highly brittle means it has a lot of implications and catastrophic failure, etc., because you will not get any warning that the material is about to fail. So, that is a major problem with this cast iron. So, now if you look at the graph on the right side, you will see UTS stands for ultimate tensile strength. Okay. Ultimate tensile strength. Okay. UTS stands for ultimate tensile strength, and you can see here this is carbon equivalent on the x axis or abscissa, and the ultimate tensile strength on the ordinate. What you see here is, and also you should think about that we are talking about only this range in this graph, that is about 3.4 to 4.3 or something percentage of carbon. It is not like from 0 to 4.2. Okay. That when you look at, the properties are going to be very different, and here we are talking about just this small range from about 3.4 to 4.2, and in this range of carbon content, how the variation in the range will change the properties. So, you can see here, let us look at only one case here. I am going to take this triangle case. Okay. At 3.4% carbon, the strength is about let us say 350, and when it reaches about 4.2, the strength decreases to about 200. You can say this is about 200, right? Okay. So, about 150 megapascal reduction in strength when you change the carbon content from, or when you increase the carbon content from 3.4 to 4.2, very small, 0.8 some difference, right? It is 0.8% difference. So, it is very small variation, but it has huge impact on the strength properties. So, that is where it becomes, metallurgists will have to be very careful while making, in controlling the composition. Okay, I just got this image from the internet, but I am not going to cover all these different cases, and here the idea of showing you this graph is only to show that there is a significant reduction in the strength as a function of increase in carbon content in this particular range. Okay. So, just to show you the importance of the percentage of carbon on the strength of the material. Now, there is another property, in the cast iron we talked about that the brittleness is the very big problem or negative, or unfavorable property. So, engineers actually worked on how to change or increase the ductility, or rather decrease the brittleness. So, they came up with some new product which called ductile iron, okay, ductile iron, okay. Now, it is more ductile or less brittle than the gray cast iron. Now, why this is becoming more ductile is because it has a different type of carbon, or the microstructure is different. You can see, let us look at only the first picture here, this one. This is about gray cast iron. You can see these flaky like black lines on that and the flaky graphites. Okay, this we covered earlier in the module on nature of materials, but let us look at again. So, these are flaky, you can see all these black lines here. So, imagine when there is a crack formation or something along those flaky black graphite, what will happen is the crack will propagate very fast. Okay, stress concentration will happen and then crack will propagate very fast, and that is why it has very high brittleness. Whereas on the ductile cast iron on the right side, you will see that they have this spherical graphite or globular graphite. Okay, so in such a microstructure, crack propagation is not as easy as in the case of a cast iron where it has flaky graphite. Okay, so spherical graphite, and in the first case in the case of cast iron it is flaky graphite. So, because of this spherical nature, it helps in preventing the progression of the cracks, or crack propagation is it's more difficult in the when you have spherical graphite as compared to flaky graphite. So, that is why it has ductile behavior as compared to a cast iron. So, we call it ductile iron because essentially this is the major difference between these two, and it is achieved by changing the manufacturing process. So, from outside it still looks more or like similar. You can't really make out whether a pipe, when you see whether it is a ductile iron or a cast iron, it is quite difficult to make out unless you look at into the microstructure of that. Now, think about these pipelines, long pipelines. Let us say there is some cavitation or something happening to the base of these pipelines and it starts sinking. What will happen is the pipe might deform, right? Say local sinking or something, if it happens, that locally the pipe might deform. So, if the pipe is not ductile enough, it will actually crack. Okay, so you really need a ductile system or a flexible system rather, if you want to call it that way, but it's more easy for you to understand. So, either ductile or more relatively more flexible as compared to the cast iron. So, nowadays you will see that ductile iron is more preferred than cast iron products, especially when you talk about possibilities of deformations. Okay, and you want structural systems like even these pipes to deform but not crack. Okay, so that's the idea. Deformation is okay, but it should not crack, and the liquid which is flowing through, that will, if it is cracked, the liquid which is flowing through, that will leak. So, that we do not want to happen. So, we want ductile structures and we do not want structures to be of very brittle in nature.